function here, and pretty easy to tell that you're going from left to right. We're always reading from left to right, and except for at 0, that's the only time my skis are horizontal. But it's not called a local max because as I go a little bit to the right, I'm already higher, right, than I was at the origin. But we'll talk about that more. But all I want to do is I want to put a point on this curve. So a comma f of a. And I want to attach the tangent line to that point, right? So tangent line would be what? Y minus what? Yeah, f of a or y1, right? And then the slope is f prime of a times the quantity x minus a. So now I got my tangent line attached, right? And so I can see my tangent at any point. Now, what does the derivative tell me about the tangent line? It tells me the derivative. What part of the derivative tells me the slope? It's the height, exactly. The height of the derivative function tells me the slope. So I want to put in my derivative function here on my sketch as well. So I'm going to type in y equals f prime of x. And just because I want it really to stand out, I'm just going to make that dashed. And what I want to do is I want to ghost the height. I want to ghost the height, the slope at that point onto the derivative function. So meaning I want to plot the point a comma f prime of a. So now you can see where my tangent line, the value of the slope, the height on the derivative, right? And it should be kind of obvious on this whole right-hand side of the function, I'm getting positive slopes, right? In fact, if I go to the left side of the function, I'm still getting positive slopes, right? You see that? The derivative is showing me the height of the derivative is the value of the slope on the tangent. So what we're noticing about this original function is it's increasing. And that means the derivative will be positive. And I've got positive slopes. My function's increasing. And the derivative is positive. And what we're going to be doing for this first derivative test, I'm kind of teaching it to you backward. I want to use this knowledge, just looking at this, to make my first derivative test simple. In that, I'm going to be saying, hey, right, if f prime of x is positive, then f is increasing. So this is our first little thought we want to have about this first derivative test. If the derivative is positive, then the original function must be increasing. Now what we did is we worked it backward. We said, hey, look at the function. Where is it increasing? And now let's look at the derivative, right? So we're going to use the information from Desmos to help us through the calculus. So we're going to test second derivative to positive or negative, and that will tell us something about the function. So this is our whole first derivative test right here. That's the main thing. If f prime of x is greater than 0, the function is increasing. If the derivative is less than 0, the function is decreasing. And we want to find those intervals, like we did in pre-cal. Remember the sign tables in pre-cal? Where you had the grid with the factors in it and the test and the column separators. You remember doing those horrible things in pre-calculus? Chrissy, yes? But we do them a lot easier here in calculus. So this is the part of my first derivative test. And sorry, there's one other part here. This is the second part of the first derivative test. If a c f of c is a local max, then the derivative has to change from increasing to decreasing, and that point it has to exist, right? So you can see positive slopes on the left of my max, and then negative slopes on the right of the max. So I'll give you a second to write those two things down. When I'm working on my formula sheet for chapter 4, I want all of this on it. Because the process that we're going to do is easy, right? But actually remembering what to do is not easy. Yeah, I'm gonna write this step by step out so that everyone copies it. But I have two parts of my first derivative test. I'm looking for increasing or decreasing intervals of the function, and I'm looking for local min or max. So this green box and the other green box are kind of my rules, right? And if you start reading 4.3, right, you'll read the book's version of it. I'm just too lazy to write it again, so I'll just have you copy it. Of course, you can take a photo if you want. What the hell does this mean? The y value is what? A number. Yeah, some number. Right? It can't be infinite. It can't not exist, right? Okay? Jadri, almost? Yep. Do it almost? Yep. So, like we already learned 4.2, absolute min and max, and we had a big checklist for that. So, for this test, your formula sheet will be packed with how do you do these problems, IPSA. F of C says is a real number. That's what it says. It belongs to the real number. So the other choice would be complex number. Hell no. Doesn't exist. No, that won't work. Or unbounded, right? Infinite. I guess it's infinite. Plus or minus infinity doesn't exist, so it's not a number for sure. Okay, so here we go. First derivative test. Step by step. First thing I want you to do is graph f of x, right? Desmos, your calculator, whatever. And you want to notice our conclusion. I want you to notice the conclusion. Do you see any increasing or decreasing intervals? Do you see a local min or max? Right? Because that's what you're looking for. You're going to use calculus to find it. Even though you can just look at the graph, I want you to use the calculus to find it. Okay? You should see the domain as well, because the domain is going to be key to us. If I have if I get my derivative, the derivative could have a different domain than the function, but I don't care about that domain. I want to care about the function domain. So graph it, take a look at it, look at the domain, right? Find the derivative. Second step, find the derivative and the critical values. And so this is what I've been training you all along to do, to have things completely factored. When you give me functions, I want them completely factored as a single fraction, single numerator, single denominator. In Calc 2, we'll start to take that restriction off. So in Calc 2, when we're undoing derivatives, we don't care so much about having a nicely factored antiderivative. So find f prime, find the critical values. By the way, what are the critical values? When f prime of x equals 0, that means numerator equals 0. And when f prime of x does not exist, that means denominator is 0. Yeah. Good. We're going to create a number line using the domain and the critical values. So this is just an example I have for ln of x, right? So ln of x, I can't put in a 0 or negatives. So the domain is from 0 to infinity, open. And the critical value is, the derivative is 1 over x. But the only critical value there is 0, but it's already not in my domain, so I don't care about it. And this will make more sense when we start doing problems, okay? So just be patient with it, right? Add in your own meaning into your formula sheet. Oh, make sure you do this, or, right? Step 4, we're going to find test values. Yep, you're still on number 3? All right, I'll wait. For the criticals, here, it says f prime of x is 0, gives me criticals. And that's when the numerator is 0. F prime of x does not exist, that's when the denominator equals 0. Yeah, that denominator doesn't look right. So after we get our criticals, we create our number line. That will make more sense when I do it. I'll show you one real quick. I'll go right back to this. So here I did my number line for x squared, right? Oops. So x squared is my function. 2x is the derivative. X equals 0 is my critical. So I have to, so you can see my domain and my criticals here, right? So that's the idea. Okay, step 4, use test values left of, right of, and in between all the criticals. Test values left of, right of, and in between the critical values. And we're getting the sign of the derivative. It's called a first derivative test. So we're testing things in the first derivative. We already know the answer from Desmos. Yes, Ipsa. Test values. Again, it will make more sense when I do a problem, okay? And then finally, we're going to make a conclusion. So you're concluding about increasing intervals, decreasing intervals, and local min and max. Let's start nice and easy, okay? Ready? Almost. Yep. What is that? Yep. Make a conclusion about increasing intervals, decreasing intervals, and local min and max. Okay, here we go. First example, nice and easy. Let's say f of x is x minus x cubed. So we want to graph it. It's pretty clear their domain is everything, right? We can go to Desmos, I guess. Yeah, you can see the domain is everything. Ipsa? Which one? Which step? Conclude about where is f increasing, where is f decreasing, where are the local mins and maxes, based on this first derivative. So definitely we see it decreasing here and here, right? You agree? In green and increasing in blue. Yes, you agree? And you can see a local min, right? And a local max. So we know the answer already. But again, what am I trying to get you to do? I'm trying to get you to use calculus to verify what you obviously know about the function because we have the technology. But I want to show that the calculus gets me the same results. Okay? All right, first step. Derivative, yes? What is it? 1 minus. Nice. And so we could factor that more, but I can just solve this for my criticals. Right? F prime of x equals 0 implies that 1 minus 3x squared equals 0. That gives me what? X squared is 1/3. Or x equals plus or minus square root of 1/3. Or square root of 3/3. Either one is fine. Just looking at those two values, that's why I like to use this function notation, right? I can do square root of 3 divided by 3 comma f of that. So I get to see, you see what I mean? I can do things before I go and do more algebra or arithmetic or calculus. I can make sure that I'm seeing that I've got the correct criticals, right? So you see here, I graphed that point without even knowing what the y value is. When I get to my conclusion, I'll find the actual y value, okay? Yes, making sense? Anybody? Yep. Nice. Once I find my criticals, I want to create my number line with my domain included, right? So domain from minus infinity to infinity. And I've got my minus rad 3/3, and I've got my plus rad 3/3 as my criticals. And I'm going to pick test values anywhere left of, right of, and in between my criticals. I tend to be pretty simple about this. So I know I can pick a -2. I know I can pick a 0. I know I can pick a 2. Now what I'm saying, remember, I'm putting these test values into the f prime, right? I'm finding f prime of -2. I'm finding f prime of 0. I'm finding f prime of 2. It's a second derivative test. I'm using the test values in the second derivative. I already know the answer, right? The derivative is negative here, positive here, and negative here. How am I doing that? I know when the function is decreasing, the derivative must be negative. When the function is increasing, the derivative must be positive. When the function is decreasing, the derivative must be negative. So I can tell those things from the graph. I don't have to plug it in, but certainly I can plug it in as well. F prime of -2 is 1 minus 3 times -2 squared. It's 1 minus 12, so -11. So I could plug them in, and I could use Desmos to plug them in too. I don't have to do it by hand, right? But what I'm saying is you can cheat it by looking at the graph. How are we doing? Question? Anywhere left of, right of, and in between, because, take a look at my graph. If I go back to, if I put my derivative on here, right? So what was it? Y equals 1 minus 3x squared, was it? Right? And I go to my table there, and I pick anything left of that low point on the green function, right? -2, you see it's got my -11. If I pick -3, -26, it's no matter what I pick from that point on, it's going to be negative, right? All right, conclusion. We're okay? Everybody's okay? Say again?
Sorry, I was on.
You okay?
Yeah, no.
You need me to go somewhere?
Yeah, because like you know how there's the A point and then there's the A prime point.
Yes, but
I was looking at the A point and it was -2, and I was like,
oh, it's a different. Yeah. So our conclusion here is since f prime of x is negative on the interval from -infinity to minus rad 3 over 3 union rad 3 over 3 to infinity, we know f of x is decreasing on I. So again, when I first start the problem, I'm looking at f to tell me something about f prime. But now, once I have my f prime test done, I'm using f prime to tell me something about f. Does that make sense? I'm using the derivative to tell me something about the function. Since f prime of x is positive, on minus rad 3 over 3 to rad 3 over 3, f is increasing on that interval. And I just change up my verbiage because my language because I get bored. But you know, as long as you're telling me that f prime is telling me something about the function, that's what I want. These problems aren't difficult, but they're pain. They're annoying. There's no way around it. I want you to be able to do these tests. Since f prime of x changes signs from negative to positive at x equals minus rad 3 over 3, and f of minus rad 3 over 3 which is hideous, isn't it? It's an interval. So I find the y value in the original function f. Even though I'm using the second derivative to test, when I want to find the local min or max, I have to go to the original function. I think I got that right. So since f prime of x changes signs from negative to positive at x equals minus rad 3 over 3, and f of minus rad 3 over 3 is negative 2/3 over 9, we know minus rad 3 over 3, comma, negative 2 rad 3 over 9 is a local min. Anybody else get the same y value there? I want to just check it real quick. Yep. Yeah, you with me? Since f prime of x changes signs from positive to negative at x equals positive rad 3 over 3, and f of positive rad 3 over 3 equals 2 square roots of 3 over 9, we know rad 3 over 3, comma, 2 rad 3 over 9 is a local max. Boom, done. A pain in the whatever, right? So if you start to look at problems in section 4.3, every problem asks you for first derivative test, second derivative test. All I want you to do when I give you the suggested problems is do first derivative test only. And then I'll assign one problem with the first derivative test and one problem with the second derivative test. Second derivative test is even longer. Question? Do it. Oh. So, is anything we just did difficult? No. But remembering what to do is difficult. So you want this step by step on your formula sheet. You should be running out of room soon. So you've got to decide, am I taking something off? Or am I writing smaller? Right? Something like, et cetera, et cetera. Yes. No, you don't have to. You know, the only thing you have to do as a human is die. And I'm a procrastinator. I'm putting it off to the very end of my life. So you don't have to write any of this. I don't have to give you the grade, right? It's easier for me to grade your page when you leave it blank. So, but that's what I want you to do. You're going to get an A, you're going to write it out. But you're going to have it step by step written on your formula sheet. And if you practice enough, you won't need the formula sheet. Let's do another one. We ready? No? Okay, I'll wait. All right, this is number number 63. Yeah, question?
So that means that like even if like f prime of x is decreasing, but it still doesn't.
Okay, but the function would be decreasing. F prime of x would be negative. When the first derivative is negative, the function is decreasing.
Like I meant like let's say like if f prime of x is positive, but it's decreasing, like the function.
No, it can't. So you're here's again. Look at this. This is the thing that I'm just telling you. This is my first derivative test. If the first derivative is positive, then the function's increasing, right? So you can't. They're not interchangeable. You can't just right. And you'll see, because remember, when you're looking at your function and it's increasing, the slope has to be positive, which means the derivative is positive, right? All right, let's do this is number 63 and 4.2. The suggested problems I want you to do in 4.3, not 4.2, 4.3, 1 to 67 odds I like, okay? And I will assign one for homework soon. So 4.3, 1 to 67 odds. So we're doing 4.3, number 63. So f of x is the ln of 1 minus the ln of x. Well, I already know something about the domain, right? But I want to kind of look at the function here. So the function's looking something like this. It's not perfect, but close enough. And so you can certainly see issues with the domain just with the ln of x. I can't put in a negative or a 0, right? So everything over here is out, including the axis, right? I can't put in negatives or 0 into that ln of x. But that's also true inside, right? So I must know that 1 minus ln of x has to be bigger than 0. So ln of x has to be, minus ln of x is greater than negative 1, or ln of x is less than 1, raising both sides base e, I get x's are less than e. So I have to be between 0 and e exclusively. Is that making sense? So I already know when I draw my number line, I'm just going to go from 0 to e, right? Oh, stupid thing keeps coming up. When I draw my number line for my test, I'm only going to go from 0 to e. Question, do it. Ln of x. No. If you look at the original ln of x, there's a piece of it that's under the axis, yeah. So I'm just thinking about the domain. What about the increasing, decreasing, and local min and max? Looks like it's always decreasing, right? Do you agree? And no min or max. So my derivative, my first derivative test, should always be negative. Let's find the derivative. So I need the inside prime over the inside. So I get 0 minus 1 over x over the inside. Or 1 over x times ln of x minus 1. Now I'm going to graph that function. And I only need to look at the domain of the original function, right? So I don't care about this other piece of the function that's to the right of e. I only care about the piece that's between 0 and e, which is in purple there. And notice where it is. It's under the x-axis. It's negative. The whole time it's negative. Yes, you with me? So we're going to do our test value. It looks like 1 is a pretty good place to test. I'm just picking anything between 0 and e. I can plug it in. I don't need to, but I can. I get 1 over 1 times ln of 1 minus 1. That's 1 over negative 1, so it's negative 1. So negative. So my derivative is negative the whole time on that whole interval. How we doing there? Yeah, we're okay? Yeah, I took this negative. I fed that one into the error. I wouldn't mark you as wrong if you didn't do that. I'm just going from that computer scientist piece that I've written that negative sign one less time. That's all. All right, conclusion. Since f prime of x is negative on the domain of f, we know f is always decreasing. Done. Not too bad. So there's a bunch of problems in there, right? You certainly can start working on them. On problems that I just suggested, Molly, listen to me please here. On the problems that I wrote on the board today of suggested, I don't care if you write them, scratch them in the dirt, or just do them in your head, but the ones that you're turning in for homework, right? I want it to be perfect, right? So, and again, where is the homework? In the textbook. So I open up the textbook, right? I open up section 4.3. I go to 4.4 and then go back a page to get to 4.3, right? And I'm looking at numbers 1 to 67 there. So that's where the homework is. Molly, yes? Molly? It's in the textbook, Molly, yes? I gave you the problems in the email. I sold you 3.7, number 59 or something like that, right? And I'll do the same thing when I'm ready to give you more homework. But I gave you suggested problems in 4.2, didn't I? In 4.2, I believe I said up to 71, maybe not. Up to 61 is fine. So suggested problems so far in 4.2 is 1 to 60, I forget already, 61. And in 4.3, 1 to 67 odds. Right now, 4.3 says, hey, do first derivative test and second derivative test. I'm saying no. Right now, just practice the first derivative test, okay? All right, let's talk about Newton's method. Let me stop the recording and make a brand new one for Newton's method.